basically, I think we've talked a lot about data-centric architectures, but I think there are two other things, like data-driven, data-aware, and I'd like to put them out because I think these are not just buzzwords. I really believe that we really need to make architectures more data-driven, meaning more learning from their past actions based on data, and more aware of the characteristics of data. So let's take a look at what we mean. I mean, this is obvious, I think. And data, I've given you a lot of examples where data overlaps machines. And so how do we handle data well? Let's skip this. Okay, let's take a look at this one. So basically we looked at architectures that are processor-centric. Today's architectures are processor-centric as opposed to data-centric. As a result, we have a huge data movement problem, right? So we need to design more data-centric architectures, and I've already shown you the slide. So we're done with that. So let's take a look at the second one, which is this one. Basically, we're not good at taking advantage of vast amounts of data that's available to the architectures. Usually, architectures make human-driven decisions as opposed to data-driven decisions. I'm going to give you examples from memory controllers over here. So let's take a look at this one. So basically, today's system architecture or hardware architecture design is very much human-driven. Humans design the policies. Humans dictate how a memory controller should operate, right? But humans don't really have, I think, the capability to reason about so many different dimensions. But I believe learning techniques have that capability. That's what this is about, basically. As a result, because humans, we don't have that ability, we have many too simple, short-sighted policies all over the system. So we don't have automatic data-driven policy learning in many of our controllers. Caches, processors, memory controllers, SSD controllers, even the most sophisticated controllers we have, they do not learn in the end. There's almost no learning. They cannot take lessons from past actions, right? So the key question is, can we somehow design fundamentally intelligent architectures? So what does this look like? I think this needs to be data-driven in the end, not human-driven. Machine learns the best policies by observing the data, observing its state of environment, learning from its past actions. So this hopefully leads to sophisticated, workload-driven, changing, far-sighted policies, as opposed to you look at some parameters over here, make a decision, and you have no idea how it will affect 5 minutes from now, right? Same thing, right? You have all this information that you could potentially harvest in the last 5 minutes of execution. Today we're not harvesting any of it. Memory control is designed by a human. You still look at the row buffer, you look at the bank, and then you ignored everything else that has happened over 5 minutes, let alone 5 years in the system, right? So that's a huge waste, I think. We're wasting all of this information that we could harvest. Basically, we don't learn in the controllers today. All controllers, I think an intelligent architecture has all controllers intelligent data-driven agents. So how do we start is the key question. I think there's a huge opportunity over here because there's so many of these examples in the system. So we need to examine the controllers. I'll give you our story very quickly. We did this work actually 12 years ago. We basically wanted to look at memory control, and we knew that memory control design was very difficult, and we wanted to schedule requests to maximize performance. And memory control design is actually very hard. I could talk a lot about this. I guess I have 1 minute to digress. But basically, you need to do a lot of these things. You need to obey a lot of DRAM timing constraints. You need to keep track of many resources. You need to handle DRAM refresh. DRAM refresh has some elasticity. You don't have to be scheduling refreshes at very rigid intervals. You have some elasticity in the sense that you can schedule some refreshes early, some of them late. And this is very important for performance, actually. You need to manage power consumption. You need to optimize performance and quality of service. Writes need to be handled differently from reads. So if you look at this, and if you're a human designer designing a memory controller, it's basically a mess. I've designed a bunch of memory controllers, and I know people who design memory controllers. In the end, all of them end up with very simple policies because you cannot really get out of this mess. And actually, I have a story related to this. How many of you know the name Chuck Thacker? Chuck Thacker? No? Turing Award winner, 2009. He designed a lot of the early personal computers, the Alto computing system. I would recommend you take a look at it if you're interested. So Chuck was a technical fellow at Microsoft when I started working on memory controllers in the computer architecture group. And he was designing the DDR3 controllers of the B3 engine, Berkeley emulation engine at that time, and an FPGA. And this person has a lot of system design experience. And he said, this is the worst thing I designed in my life. Because there's so many things, so much mess you need to keep track of. And in the end, you're optimizing for performance, right, or other metrics. So I think this is exactly what we had in mind when we first started looking into memory controllers also. Basically, these are some example timing parameters. They're not sophisticated. They're all there for good reasons. But even optimizing for 5, 6 timing parameters is not easy, basically. How do you come up with a scheduling policy, let alone for 100 timing parameters? If you're interested, these are some papers that you can look at. And this problem is going to get even worse into the future. It's not just timing parameters, it's also different requirements of the agents. It's also different requirements of different memories. Basically, you have this memory controller that needs to optimize for many metrics, and the human is designing this. I think this is a terrible thing to do, frankly. So our dream at that time was get rid of the human, in the sense that get rid of him or her as much as possible, because they have too many things to think about. And even if you perfectly optimize a single workload, once the workload and the system changes, the policy becomes not so good in the end. So we wanted to actually treat memory controller as a machine learning agent that automatically finds a scheduling policy on its own. So this is the idea. I'm going to go into a little bit detail, but not a lot. So this is the problem. We want memory controllers that are easy to design and that are still good. And the idea is to have a memory controller that adapts its scheduling policy to the workload behavior and system conditions using machine learning. And the key question, of course, always is what kind of machine learning agent that you implement. And I think the jury is still out. I believe there needs to be other machine learning approaches to be examined. But we found out at the time that reinforcement learning is a very nice machine learning algorithm that maps nicely to memory control, because reinforcement learning usually operates on Markov decision processes. Basically, if you can specify your system as a Markov decision process, then you can actually prove things about your system, and reinforcement learning can converge. And memory control is a Markov decision process. Basically, all of us are reinforcement learning agents also. I assume a lot of people know about Pavlov's dogs, right? Those are reinforcement learning agents. Basically, the dog learns to associate a system state, I guess the bell ringing with the food coming, assuming it takes a particular action, right? You have the system state, bell rings, the dog goes to the master, I guess licks their hand, and then gets the food. So in a given system state, you take an action and you get a reward, and you learn that. Basically, memory control is very similar to that. Basically, it's a reinforcement learning agent that can optimize for long-term decisions. And a reinforcement learning agent looks like this. You observe the system states, you take an action, and you get some reward. And over time, you figure out which actions to take given a system state to maximize the long-term rewards, not the short-term rewards. And you can specify the reward function so that you can maximize a very long-term reward structure. That's the idea. So in DRAM, you could do this. Basically, if you want to maximize data bus utilization, long-term data bus utilization, you have some state that you observe, and you schedule a command that maximizes the data bus utilization. So the key is learning which commands to schedule in a given system state so that you maximize data bus utilization. And you need to specify a reward function, you need to figure out what state attributes to look at, and you need to figure out how do you learn. Clearly there's a lot here that I'm not going to go into detail, but basically you associate system states and actions with long-term reward values. Each action at a given state leads to a learned reward. And you schedule the command with the highest estimated long-term reward value in each state. And basically by observing the reward values, you continuously update the state action pairs based on feedback from the system. We use Q-learning in this case, but if you're really interested in reinforcement learning, Richard Sutton, who's really the father of reinforcement learning, has written a book, the book of reinforcement learning, and he recently updated it in 2018. And it's a PDF on his website, so you can actually download it and learn a lot about reinforcement learning. So this is one example, clearly. And this is what the human designer needs to do, basically. They need to specify the reward function. They need to specify the state attributes, but you could also learn these state attributes. I think in our case, we did a lot of simulation to figure out the state attributes. And you need to specify the actions. And I think these are a lot simpler. Reward function can be tricky, of course, but it's much more simple than coming up with a policy that's good at many possible metrics. Okay, and we showed that you can actually get large, robust performance improvements over many human design policies in this case. And I think this is really scratching the surface. I'm talking about this because this is a concrete personal example of how you can make controller and system design much more learning-driven, data-driven. So clearly, with any other idea, you have upsides and downsides. These are the upsides. You continuously learn. You're more robust. You reduce the designer burden. Now the design needs to specify what system variables might be useful, what target to optimize, but not how to optimize it. How is usually very difficult, I think. These are a bit easier. Also, I think you can learn some of these system variables. I think it's very difficult to learn the target to optimize, frankly. It's too semantic that Who knows, at some point. Maybe that's what makes us different from machines right now. We learn what target to optimize better than machines today, but maybe 10 years from now, they will learn what target to optimize, and we may become the targets. I'm just kidding. Okay, how do you specify different objectives? I think there's a lot more work to be done in this area. How do you specify different objectives? What is the hardware complexity? And I think also a mindset in the design. We need to change the mindset, because the mindset in design today is human design policies. We don't really have a design tool flow for machine learning or learning operated policies also. I think this requires some more thinking, of course. I just put it out here, but I think our design flows need to change to really enable these learning-based controllers. If you're interested, this is the paper that talks about it. Okay, so I think an intelligent architecture. Basically, we need to rethink the design of all controllers that we have in the system. And there are a lot of controllers, actually. Okay, now let me give you the last one over here before we conclude. And I think I'll leave you with the concluding slides. But basically, this is also very important, I think. I'm going to spend even less time here, because I think we know even less here. Basically, today's architectures don't know about data enough. They treat all data as the same. As a result, the decisions that we make are more component-aware decisions as opposed to data-aware. Now, what do I mean by this? A data-aware architecture really understands what it can do with and to each piece of data. Basically, it's aware of the characteristics of the data. Now, let's take a look at some examples. Basically, we want to use different properties of data to improve performance, efficiency, and various other metrics. Now, what are the properties of data? There's a lot of properties. These are some. Maybe you can come up with others, right? Compressibility, approximability, locality, sparsity, how critical is for computation X, Y, Z, access semantics. There's security-related properties. There's privacy-related properties. I'm not even talking about those, right? There's so many properties of data. But today we don't communicate. We may know some of these properties at the higher level, and we can discover some of them if we want to. But certainly we don't communicate any of them to the hardware. Now, that's not exactly true, because we communicate very small examples of locality, for example, with very specialized interfaces, like a specialized instruction, non-temporal prefetch instruction. This is an example. It basically tells you this is a non-temporal load, so you should not cache it, right? There is a very small aspect of locality that gets communicated. Sometimes some other things may also get communicated, but we don't really have a general interface so that we can provide this higher level semantic information down to the lower level of the hardware, because once you communicate it, the hardware can do many things with it. So basically, we have limited interfaces. There's a lot of information visible here, but we funnel them through a very simple general purpose interface that loses a lot of that information. So we want to actually enable a lot of that information down to the hardware so that the hardware can actually take advantage of that semantic information. We call this expressive memory. I'm not going to talk about this in detail. This changes the architecture a little bit, but you can take a look at the paper. I'm not going to talk about this in detail, but the paper is interesting to examine. I think this is very interesting to do more work. But I'm going to show you an example table from this paper. This is one table. And basically we show examples of example semantics that can be communicated through this interface, expressive interface, from the software and the programmer all the way down to the hardware. And you can improve cache management, page placement, more compression. I like compression a lot. Data prefetching, other stuff, approximation, ... Now we were clearly thinking a lot about the memory system, but you can add more to it, I believe. Let me pick one. Compression is actually very interesting, I think. Today, systems, because they don't know information about the data, like the data types, like the properties of the data, sparsity, pointer, data index, compression algorithms are actually very general purpose. But if you actually communicate all of this information, you can make them more special purpose, and you can adapt to them. And that way, actually, you're much more efficient. So this is one example. But I think what we're imagining over here is just scratching the surface. There's a lot more to think about, and you're all creative people, and probably you can come up with something better over here. Who knows? So we actually showed a bunch of concrete examples in our work. So this is non-details work. The previous paper was more general. This one's on GPUs. It's much more specific, and it's much more specific to the locality. But this is one example of these expressive interfaces where semantic information about the locality of data structures, locality of accesses from different threads can be communicated to the hardware. And this paper actually shows that you can get significant performance improvements if you communicate locality characteristics of different data structures and different threads and the GPU takes advantage of it to do the mapping and caching policies, you can get significant performance improvements, more than 60% or so. And this idea is actually currently being implemented by NVIDIA in their future GPUs. So this sort of ideas can be adopted, especially in specialized domains going forward, but we really want to make it general purpose also, because I think this is really scratching the surface in the end. So another example is hybrid memory management. I think if you know the properties of your data, you can manage these memories much better. Today we don't know. As a result, we need to somehow discover, but we cannot discover really well in the end. And this is another, actually, this is another example of expressive memory, what I discussed. Somehow, at that time, we were very specialized, of course, basically identifying characteristics of data that's semantic, like this, vulnerable and tolerant. You can enable very different type of memory system designs that are much more scalar. Maybe a small amount of your memory has to be very reliable. A huge amount of your memory can be very low cost, right? And of course, you can enable other benefits, and I've already talked about this, so I'm not going to talk about this more. But this is it's an example of a data-aware architecture. Very simple, specialized, but if you actually have a very expressive interface, you can communicate a lot more information about data. And I think this has a lot more room for innovation. This is also good for enabling processing in memory, in my opinion, because processing in memory, you can tell, for example, based on the characteristics of the data, whether you're amenable to processing inside one memory structure or some other memory structure, or where you should process the data. This could be used as hints through these expressive architectures. Okay, so basically I think this kind of completes the picture. Basically, we don't want to be just data-centric, but we want to be data-driven and data-aware. And I think these are all orthogonal but related issues. And maybe then we can approximate something like this. I think we're just too far away from this, because this is definitely not processor-centric. I don't know enough about this for sure. I don't think we know collectively enough about this, but I know for sure that this is not processor-centric, and I know this is doing more learning than what we do, and I don't know about the data-aware characteristics that I cannot speak about at all. Probably it's data-aware, but I cannot tell how. Okay, but I think to get there, we need to really think across the stack, right? But we need to get there step by step. Okay.